Today you will learn how to balance a chemical equation. But before we start, what is a chemical equation? A chemical equation is a written description of what happens in a chemical reaction. In this equation, on the left side, you will find the reactants. The reactants are the starting materials or the initial substances found in a chemical reaction. The arrow indicates the direction of the reaction. Now on the right side of the equation, you will find the products. The products are the substances made after the reaction is completed. When you write a chemical equation, the two sides of the equation should balance, which means that there are the same numbers of each type of atoms on the left side of the equation as there are on the right side of the equation. Take a look at this equation. Remember that the reactants are on the left side and the products are on the right side. These numbers right here are called subscripts. They indicate the number of atoms of the given element. You will see that this equation is unbalanced because on the reactant side there is 1 atom of iron and 2 atoms of oxygen. On the product side there is 2 atoms of iron and 3 atoms of oxygen. Now how will you balance this equation? So to balance this equation, let's first write how many atoms of each element are present on each side of the equation. Keep in mind, if there is no subscript, it means there is 1 atom. So there is 1 atom of iron and 2 atoms of oxygen on the reactant side. On the product side, there is 2 atoms of iron and 3 atoms of oxygen. When balancing equations, you never change the subscripts. You only add coefficients. Coefficients are whole number multipliers. For example, if I put 2 in front of this compound, it will change the total amount of atoms this compound has. 2 times 2 would equal 4 total atoms of iron. 2 times 3 would equal 6 total atoms of oxygen. Now to balance this equation more quickly, there is a strategy that can help you. First, you look at how many atoms you have on each side of the equation. Then you add coefficients in front of the molecules to balance out the number of atoms. Remember, balance atoms present in a single molecule of reactant and product first. Then balance any oxygen or hydrogen atoms last. In this equation, iron is present in 1 reactant and 1 product, so balance its atoms first. There is 1 atom of iron on the reactant side and 2 atoms of iron on the product side. So you might think putting a coefficient of 2 in front of iron on the reactant side would work. While that would balance iron, it would not, however, balance the oxygen atoms, which means you have to replace 2 with a higher number. I would replace it with a coefficient of 4, so then I could add a coefficient of 2 in front of the iron oxide compound on the product side, which then would give me a total amount of 4 atoms of iron on both the reactant side and the product side. Then you save oxygen for last. If you look in the product side, 2 times 3 is equal 6, which means 6 atoms of oxygen in the product side that I would have to match in the reactant side. Right now I only have 2 atoms of oxygen, so I would add the coefficient of 3 to make that equal 6, which then would give me a total amount of 6 atoms of oxygen on the reactant side and on the product side. And now you have yourself a balanced chemical equation. Now on the side note, you could have written a balanced equation using multiples of the coefficients. For example, if you double all of the coefficients, you still have a balanced equation. But remember, it is always best to write a chemical equation in its simplest form. So check your work to make sure you can no longer reduce your coefficients.
There are 5 types of chemical equations. They include synthesis reaction, decomposition reaction, single replacement, double replacement, and combustion.
Let's start with synthesis reaction. That's when 2 or more reactants form 1 product. And it can be modeled by the generic form of A plus B equals AB. So let's say I had this problem. P4 plus O2 produces P2O5. So first I would balance it. I would put a 5 over here, 1 and a 2. So next you would look at the structure. And here you see that you have two elements combining to form one compound. Next is decomposition reaction. That's when a single compound breaks into two or more simpler substances, and it can be modeled by the generic form of AB producing A plus B. So basically it's the opposite of synthesis. In my example problem, I wrote HGO produces Hg plus O2. So when you balance it, you'll get a ratio of 2 to 1. And it's decomposition because you have a compound breaking up into two elements. Third, we have single replacement. That's when an ionic compound reacts with an element to form a new ionic compound and a different element. So it can be modeled by the generic form of AB plus C produces AC plus B. Or it can also be AB plus C produces BC plus A. So in the example problem, we have AlBr3 plus K produces KBr plus Al. So when you balance it, you will get 3 Ks, 3 KBr, and 1, 1. So you have a compound here that reacts with an element to form a new compound and a new element. Except the only difference is that aluminum was kicked out all the way over here, and now both of these join together to form a new compound. Double replacement is when two ionic compounds exchange places to form two new compounds. And the generic structure for that is AB plus XY produces AY plus XB. In the example, we have PB Br2 plus HCl producing HBr plus PbCl2. So balancing that, you would get a ratio of 1, 2, 2, 1. The thing with double replacement is that it has a certain pattern. It starts right here, and it combines with the outer element, Cl2, so it's right here. Next, you start with an inner element, but start on the right side, and it combines with the one on the left to produce HBr. Last but not least, we have combustion. Combustion is when substances burn with oxygen to form common oxides. Although there's no generic structure for this, we do have a tip. You should look for CO2 in the product side or O2 in the reactants, and I'll show you through this example. So let's say you have C2H4 plus O2 producing CO2 plus H2O. So first you would balance it. So you have 2 carbons over there and 4 hydrogens. Now you have 6 oxygens, so a 3 over here. Next you look for the carbon, and you also have oxygen over here. And a dead giveaway is that you produced carbon dioxide and water. It doesn't always have to produce carbon dioxide. It's combustion as long as it produces any common oxide.
What's wrong, Juan?
We just got second place in Fortnite.
Here, want a cookie?
Oh, thanks. Dude, there's only one cookie in here.
I have some of the ingredients, but I don't know how many cookies we can make.
Dude, it's a lot like stoichiometry.
Stoico, what?
Stoichiometry, dude, let me explain. Stoichiometry is the ratio of moles of all reactants and products involved in a chemical reaction. How this is like cooking is because we know how many ingredients we have, but we don't know how many products we'll make, so we need stoichiometry to find that out. For example, we have 2 NaOH plus CO2 is turned into Na2CO3 plus H2O. How many grams of H2O are produced if there are 30 grams of CO2 being mixed? Since it is already balanced, we just have to focus on the important information. We have to change the 30 grams of CO2 into moles of CO2. Then we have to use a mole ratio to find moles of H2O, which is 1 to 1. Lastly, we multiply the number by the molar mass, which is 18.02 grams, to find the answer. Rounded correctly, it comes out to be 12 grams of H2O.
Limited reactant is the reactant that will be exhausted first.
For example, we have N2 plus 3H2 is turned into 2NH3. If there are 0.7 grams of both reactants, which one is a limited reactant? We find the moles of N2 using the 0.7 grams, then we use the mole ratio to compare it to H2. Next, we find the moles of H2 using the 0.7 grams again, and we compare the two. Whichever one of the two is smaller, it is the limited reactant.
Percent yield is the percent of the product formed during a laboratory experiment. Theoretical yield is 100% of the possible product that is formed. Actual yield is percent yield divided by the theoretical yield.
For a third example, we have our balanced equation CaCO3 decomposes into CaO plus CO2. 17 grams of CaCO3 is decomposed, but only 3 grams of CO2 are actually produced. We must find the theoretical yield, and then we have to divide it by 3, which is the actual yield, and multiply it by 100 to find the percent yield. To find the theoretical yield, we use the 17 grams given and divide it by the molar mass of CaCO3, which is 100.09 grams. Then use the mole ratio of 1 to 1 to find moles of CO2. We multiply by the molar mass of CO2, which is 44.01 grams per mole. Last, we divide 3 by the theoretical yield and multiply by 100 to find the percent yield, which comes out to be 40%. Thanks for watching, and we'll see you next time.